record. Yeah, thanks. We are starting like a whole new world. And so in some ways, like you could come into this class at this point and really not be at a disadvantage, at least for a while. Like integrals will play a role in this at some point, but primarily not anymore. Very beginning of this class, I hinted that this day was coming. And that was the day I told you that differential calculus, Calc 1, the derivative stuff was all subtraction and division. You got your definition of your derivative, right? It's difference quotient. And that this class was all about multiplication and addition. And it's really coming home now. We're going to, by the end of next week, be adding infinite sums of things. And this is where things get so strange and amazing. And there's lots of really cool sites along the way that we're going to definitely pull over the side of the road, take a look at, and enjoy. Maybe even today. I kind of want today to just be a little bit of an intro. I don't want to burden you with a lot of new ideas because you're still probably, is anybody done with the exam? Kind of, that's good. Okay, I'm glad to see that. Yeah, like mostly done. Okay, or kind of there. That's good. So yeah, I'm not going to open a web work unless you want it. Like shoot me an email if you need some web work this weekend. I am so happy to hook you up. But what that web work would be on and will be on next week is kind of an important idea that leads us into the idea of adding infinitely many things. So the first thing we're going to talk about are just sequences. And there's two kinds. There's finite, and then there's infinite sequences. We're primarily going to be concerned with these. And why would that be the case? Well, because a sequence is just a list of numbers. So what is a sequence? A sequence, I'm going to give you a couple of ways to think about this. A sequence is a list of numbers. That sounds a little trite, but it's actually very deep in a way that some numbers can be listed. Not all numbers can be listed, and that's like a really cool idea in mathematics that we don't really have time to get into. But a sequence is a list of numbers. So, for example, if I took this sequence, this list here, the way I wrote that is actually pretty helpful because you can look at that sequence, the ellipses at the end, there's usually only 3, mean, and so on forever. Keep that rhythm going. And I've established the rhythm so that you can keep it going. So there's a couple things going on here, right? And like if I asked you, what is the next number in the list? Would you be able to make a reasonable guess at what that number was? Gabe's giving me, Gabe sounds pretty good. Gabe, what is the next number in that list, my friend?
64.
That's beautiful. Yeah. So Gabe, no doubt noticed that each subsequent number is 2 times the previous number. And that's one way to think about this sequence, that I'm just taking each number, multiplying it, and then moving to that next one, multiplying it by 2, multiplying by 2. But there's other ways to look at this sequence. Let's take a look at another one here. What about this one? Just a little hint. This is a famous sequence. What? Yes, Sophie, what is that sequence?
Is that Fibonacci?
That is it. That is absolutely nicely said. Yeah. So this is the Fibonacci. I think there's 2 C's because of the Italianness of that name. That is the Fibonacci sequence. So Sophie, what is the next number in that sequence? Do you know? Like,
I think it's 21.
It's good. How are you getting that?
13 plus 8. You add whatever the prior number is to the current one.
Yeah, beautiful. Exactly. So to get to the next number, you take the previous two and add them. So 2 is 1 plus 1. 3 is 1 plus 2. 5 is 2 plus 3. And so on. So Sophie said, okay, well, that seems to be the rhythm. So I'm going to make a stab that the next number here is 21 because that's 8 plus 13. That gives me the next number. The next number after that is going to be 34. Wait, if I added right? Yeah, okay, just double check and make sure I added those right. So this sequence is like one of the most famous things in mathematics. Does anybody know any cool facts about the Fibonacci? Ooh, somebody's chiming in here on chat. Sorry, who's on my chat? 64. Yes. Oh, wait. How'd you get 64, John? Which one is that? Is that
for the earlier one that he
oh, oh shit. Okay, good. A little late. Got it. Yeah. Agreed. Does anybody know anything like legends about the Fibonacci sequence? What have you heard? Where have you seen this?
I always see the Fibonacci sequence as that big spiral shape.
Yeah, nice. Yeah, and Isaac's hinting on a related aspect of that in the chat, talking about the golden ratio. So let me address both those things. So this is kind of a fun day too. There's going to be a lot of fun days coming up, math fun. So one cool way to visualize this sequence is to think of squares being nested and wrapped around each other in the following way. So first I take a little square that is 1 by 1. So I'll just put a 1 inside. That just indicates the square side length. And then on the side of that, I attach another square of side length 1. Then underneath those, notice how I'm moving to the right and then down, and I'm kind of moving in a clockwise pattern. I now step under those two and I attach a square of side length 2. On the left side, I can attach a square of side length 3. Notice how this is getting Fibonacci as hell. On the top here, then I attach a square of side length 5, and then 8. And I'm going to keep doing this for a reason, not just because I think you need to see squares and hear me add simple things up. But let's see, so that square would be 2 plus 1 plus 5, so 8. And then, a big old 16 underneath, but I'm going to stop right there. Not 16, 13 underneath. So you keep on going and you see this rectangle forming. At every stage, I've got a new rectangle forming. I've also got the corners of these squares forming something quite lovely. So if I start at the lower left corner of the original square, and I trace my way through these intersections like this, I start to see a spiral emerge. It's a little shaky there, the way I'm drawing it. That spiral that emerges is called the golden spiral. And so that's what Abraham was alluding to, I think, pretty much, seems like, yeah. And that keeps on going forever and ever, just like this, the possibilities of adding squares onto this. The thing that Isaac was referencing, the golden ratio. So we have this number phi. Ooh, I'll do it in gold. The golden ratio phi. Anybody know what that number is? It's like, kind of shows up a lot in a lot of strange places. Anybody know the golden ratio? Okay, I'll give it to you. It's like one of those things you either know or not. You're not going to sit down and crank it out. 1 plus square root of 5 over 2. I don't quite know what that number is. Like 1.618. I don't know. I don't have my calculator in front of me. How does that fit into this? Well, if you look at the rectangles that are forming, one side will always be longer than the other. if you take the ratio of those lengths of those sides, like this one right here would be, so the ratio of the sides is going to be 13 to 8. And then if you think ahead, what would be the ratio on the next one? Well, let's see, if we added down here, we have, let's see, so we're adding a square of side length 13 down here. So this is a 13 being added. So we'd have a 21 length. 21 is the length of the big side to 13. So then the next one's going to be 21/13. Now you can kind of start to see a rhythm here. What was the one before? So the one right before that was 8/5. What's the next ratio? What's the rhythm here? This is all about rhythm finding. What's the rhythm? What's the next ratio? Oh, somebody said, somebody's got it here. Oh yeah.
The next one being 34/21.
Yes, it would. 34/21. Yes, and Isaac gave us the golden ratio in the chat there. I was right with the 618, so good for me. And then Sophie gave us this right. So Sophie, how did you get that? What's the rhythm you're catching here? Like, what's the method of getting that next one?
The numerator in the current fraction becomes the denominator in the following, and then the numerator in the following is whatever the next number in the sequence is.
It is, and you can find that by just adding the numerator and denominator of that previous fraction, right? So those we get a good old 34 up here. Let's go to Excel for a minute. So I want to show you how to do, if you don't have much Excel experience, this will be useful. If you do, good for you, because Excel is freaking amazing. Excel is so much fun. And you can use Google Sheets. If you don't have Excel, Google Sheets is free, but actually for you all, Excel is also free. You can get that through Regis. You can download the whole Office suite through Regis. And Excel is like the best part of that. Has anybody ever seen where they took Excel and programmed Minecraft into it, maybe? Something like that. There's like an entire world coded into Excel. It's just absolutely mind-blowing. Oh no, I think they created a PC. No, I'm confusing Minecraft with other things. Anyway, I'm going to stop babbling. The stuff people do in Minecraft is also incredible. So let me share the screen here. Let me get up Excel. Because I think you're going to want to use something like this. I'm going to give you a couple tools to explore sequences. So let me share my screen. Here, I'm going to share local screen. Okay, there we go. Cool. So I got Excel up here and a bunch of stuff that doesn't need to even exist anymore. So let's talk about how to create a sequence in Excel. And I'm going to show you how to do this one that we're doing right now. The first term was a 1. And then the next one was a 1. So you can look right there. I've got it listed on, well, I don't have it there, I guess, anymore, but hopefully you wrote it down. And then we added those two and we got 2. And then we added the 2 and the 1 and we got 3. But I can have Excel do this for me much faster. So what I'm going to do is say, hey, Excel, this current value is equal. You type equal. That tells Excel you're about to do computation. And it's waiting for information. So like right there, I could type equals 2 plus 3, but that would be not super helpful because I know the answer is 5 and it's not saving me any time. So what I'm going to say is equals, and I'm going to click on the cell A3 and then say plus the cell A4. So now what I've done is I've created a dynamic relationship there. Those are pointers, and it's basically saying this current cell equals 2 cells back value plus previous cell value. And I hit enter and I got my 5. Now, You're like, well, boy, that was a long way to get 5. But watch what I can do. I click on that cell and I see this little corner is kind of like highlighted here. If I click on that, hold the left button and drag down, Excel should know exactly what I want to do. And it does. And it continues the pattern all the way down. So we're seeing the Fibonacci sequence emerge right here in front of us, and to, any depth that we want. But see, right there, the precision's getting so bad, we don't even see most of the interesting digits down here in the 40th Fibonacci number. But now I can actually take these numbers and do the thing we're doing. Remember, it was ratios. So the first one's going to equal the current value divided by the previous value. So that's 1/1. And then I can just take that and feed that down. So check it out. Next one's 2/1. Next one should be 1.5. Yeah. Next one should be whatever 5/2 is, whatever 5/2 is. Yeah, there it is. Now, watch how that number changes each time I go down, and I'm being a little over dramatic about this. But notice how it's going up and it's going down, but it's starting to settle. The tens digit is starting to be, has been fixed at 6. That 100th digit seems to be fixed at 1. And the further down I go, the more digits become fixed. And so let's go all the way down to here where it's got actual decent precision. Check out the number that we're getting closer and closer to each time. And let's just check for comparison over here. Let's see. So I'm going to take 1/2 of 1 plus the square root of 5. That was the number I said was phi. And I guess I probably want your correction. Yeah. So notice that this ratio is approaching the golden ratio, phi. Why is phi important? So first off, just the craziness of this. Here's this Fibonacci sequence, which was produced by Fibonacci studying rabbits multiplying and their offspring. So he did like just some, mental work. If he puts a rabbit into a pen, so you've got like a pen, you put in one rabbit and one rabbit. After they—
You're still on Excel.
Oh shit, thanks. Thank you. You knew what was up. Nice. Cool. Yeah, I was clearly drawing there. We'll come back to Excel in a bit. So let me share this shit again. These will be stories you can tell, your grandkids and stuff. Hopefully your grandkids will care about things like this. Got it. Okay, so share content again. There we go. Or it's the weekend. Tell your friends when you're out at the bars. Okay, here we go. Yeah, we come back. So what Fibonacci was doing was studying rabbits multiplying and how the total population changed from generation to generation. So you definitely need 1 + 1 rabbits to get somewhere. They're not amoebas. That would be crazy if they were. I think we'd have a lot of rabbits in the world, but they need each other to multiply. So these rabbits get together, they have one offspring. In that next generation, then there are 3. So first generation, there's 1. We put in another rabbit. There's 2 rabbits. Those rabbits mate. We got 3 rabbits on the next one. So let's see. So we had 1. Yeah, maybe I'm fucking this up. Okay, I'm going to come back to the rabbit story. It's all about rabbits. I'm getting my rabbit counts a little off here, so I owe you that. I'll come back on it. So the golden ratio, what is that number? It is said, and the Greeks believed this thoroughly, that if you make a rectangle and it has the proportions of the golden ratio, it is the most appealing to the human eye. So in all their statues and their architecture, they were trying to imbue this ratio. So they deliberately built it in there. So like if I took a golden rectangle and I had, here's the height, here's the width to the height is phi, and that's a golden rectangle. I think there's been studies done about this that show it's a little bullshitty, but it's kind of true. And then there's like all these Fibonacci code books and stuff written about Jesuit monks and dark secrets lurking between the walls of the Catholic Church and math. So I don't know about that either. All right, let's play another game here. Here's a sequence. Ooh, let's get out of golden ratio color. So I'm going to start with 1/2. I'm going to go to -1/4. I'm going to go to 1/8, -1/16. Can you tell me what are the next two numbers in this? And just take a moment. What are the next two? This might be easy. We're taking it easy. I promise it won't always be. But we're just building up our rhythm seeking skills.
Is it 1/32?
It is. And what's the next one?
-1/64.
-1/64. Cool. And I love that two different folks chimed in on it because there's two different rhythms here, right? There's this rhythm of the bottom where I just multiply by 1/2 each time, but then there's an alternating sign as well. So what if I asked you, find a formula, and I will ask you this, find a formula for the nth term. So the pieces of a sequence, the numbers that make up a sequence are called terms. Find a formula for the nth term of this sequence. Now things become a little more challenging. So I want to give you a few important formulas to use when building sequences, because you're going to have to do this. So here's some vital formulas for sequence building, or sequence description. Maybe that's really what I mean. So the first one is this, is that if I have -1 to the nth power, so now n is going to equal a number that goes 1, 2, 3, 4, or maybe 0, 1, 2, 3, 4. This n here is called our index. And it's the thing that allows us to get to the 100th term. If you want the 100th term, you let n be 100. But -1 to the n produces alternating sign. SIGN, alternating sign. So when n equals 1, I get out -1. When n equals 2, I get -1 squared, which is +1. And then -1 cubed, -1, and so on down the line. So when you see a sequence that's going plus, minus, plus, minus, plus, minus, you want a -1 to the nth power in there. So the sequence that we see above, definitely going to need it. The other kind of weird thing, which doesn't kick in here, but I'm going to put it in here now, is n factorial. And I just want to review that because we'll be seeing it a lot. You're going to know a lot of factorial stuff that you maybe didn't before. But n factorial, this just means probably the best way to see it is maybe by case. So first off, we just defined 0 factorial to be 1. There's a lot of reasons for that. Let's just accept it. And now we can talk about it more on Monday. Happy to talk about why. I can give you like 3 reasons why. The best one is let's just forget about it right now. It's probably good. 1 factorial is 1. Now, 2 factorial is 1 times 2, which is 2. 3 factorial is 1 times 2 times 3. That's 6. I'm gonna write something slick here. Check this out. 4 factorial is actually 1 times 2 times 3 times 4. But a cool way to see it is that it's 3 factorial times 4. That will actually be a useful thing. 5 factorial is going to be 4 factorial times 5. So it's just the product of all the numbers between 1 and that number, the whole numbers. That's what a factorial does for you. So we can crank these out. 4 factorial is 6 times 4. 5 factorial is 24 times 5. And they get really big really fast. So I'm not going to even draw any more out here. So this doesn't, like I said, this isn't for this problem, but it will be for a future problem. So today, in fact, I think let's think about how to break this down. So first off, we see alternation in it. And what I want to do is I want to write a formula. So A sub n or B sub n or something sub n equals the nth term in our sequence. And that notation is going to be all over the place. Let's see, wait, I got a chat here, better check in. Oh yeah, John is definitely. So John, yeah, that's a good recursive formula. We're going to come up with an explicit one, but you're absolutely right. Nothing wrong with that formula, but sometimes an explicit one is useful in a very different way. So nth term in our sequence. Our first term, so that means a sub 1 is a half, a sub 2 is negative a fourth, a sub 3 is an eighth, a sub 4 is negative 16th, and so on. So I want to make that association. And now what I need to do is come up with a formula that allows me to move from the subscript to the output. So we have to start kind of thinking about, like, what are all the things happening here? Well, it looks like without the sign change, notice that 1/4 is just negative 1/2 squared. And 1/8 is positive 1/2 cubed, or 1 over 2 cubed. This one here is negative 1 over 2 to the 4th. And so, like John, if you notice in the chat, John's saying that, oh, to get from each term to the next term, I multiply by negative 1/2. And that is 100% true. And that's an important observation, that from 1/2 to negative 1/4, I multiply by negative 1/2. Negative 1/2 times a negative 1/4 gives me positive 1/8. Absolutely true. But we're seeking here a formula so that if I said to you, what is the 100th term? You don't have to work the first 99 to get the 100th. That's the beauty of an explicit formula. So notice here, we kind of have part of our formula down. It's going to be 1/2 to the n. That's going to get us the magnitude. And I'm going to multiply that by a negative 1, and I'm going to try to the nth power first. And I'm going to see if that works. So somebody tell me, is this formula the one I want? Does this formula cut it? So I'm getting a think so in the chat. I'm getting a thumbs up. So I guess what I want to make sure is this true? Is a sub 1 going to be a positive 1/2 for us? It is not. Now I'm saying definitely a strong no there. So it's close, but it's out of sync just a little bit. So if you check here, Isaac, I've got this a sub 1 there. So I'm already saying that the first one has to be positive. So our a subs, you got it? Okay, cool, awesome. And you're right, like if you're starting at 0, that would also work. So that's not incorrect for other situations. this one isn't right because a sub 1 is going to start off negative, right? We're going to get -1 to the first times 1/2 to the first, and that's -1/2. What can I do to modify this? So this is close, but not quite right. What do I modify it with? Let's see, I'm getting some chat action here. Ah, got it. That was me and Isaac chat.
Maybe throw a second negative in front of it.
Yeah, nice, right? And then that'll flip the parity of the plus minuses. So we could do this. Beautiful. Now it's going to work. You can check that out. That will cut it. Here's another way to do it. A sub n could also equal, now check this out, and this is a good trick to keep in mind. You can just bump the power up by 1. And now, when n equals 1, I've got a +1. When n equals 2, I've got a -1. So I just tweaked that exponent a little bit to get the parity of the plus minuses in sync with what I want. And I can
And the 1/2 wouldn't need to be +1, right? It would still just stay as n.
Yes, absolutely. 100%. If I put a +1 there, then I'll be starting off at a 4th. And yeah, so you're absolutely right.
I missed a little bit there. Can you explain why the 1/2 can't just be made negative?
Oh, okay, it can, and it actually, I was just about to do that one. So we can do this, and I think that was Sophie, right? So, yeah. So we can do this. So here's another possibility. But notice that when n equals 1, I got a negative, so I just got to make sure to tack a negative on the outside just to get that parity. Any one of these formulas, any one of these 4 formulas, 3, sorry, this one's not quite legit. Any of these 3 formulas, it's going to get it done for us as an explicit model. John had suggested this one. So let me just put what his suggestion was, that a sub n is going to equal -1/2 times a sub n minus 1. Let's look at that. This is the other way. So this down here, this is explicit. This is recursive. So this is the recursive description here. And let's talk about that for a minute, because that's also a lot like that Fibonacci sequence we were talking about, right? So let's go to this really quick. Let's see. So our sequence is this. And then our suggestion was this. And let me just show you another way to write that is this. This is completely legit too. It's indicating the same rhythm. It's just saying the next. So you can think of this as the previous, and this is the next. This is the previous, and this is the next. So notice those are both completely okay. Here, well, I guess in both, n is going to run from one. We just got to be a little careful here. So let's say n here goes 1, 2, 3. And so you want to let someone know what the range of the n values is. What are the possibilities for n? But you need to let them know one other thing. Where to start? This thing doesn't have a root to begin with. So like, check this out. When I put in n equals 1, I get a sub 1 equals -1/2, a sub 0. Oh shit. What's a sub 0 going to be? So this one's a little bit off the way I'm writing it, because it's referencing a sequence term that I may or may not have talked about. We could call this one a sub 0, this one a sub 1, and this one a sub 2. It kind of looks like that's what we're doing here. In the end, it doesn't matter how you describe it, as long as the description is legit. There's usually like infinitely many ways to do it. So lots of options. But here I need to set the initial value. So with any recursive sequence, you have to initiate it. Set the initial value. And so we're going to say a sub 0 equals 1/2. And then notice that a sub 1 would equal -1/2 times a sub 0. That gets me my -1/4. And so now we're kind of going back to what Isaac was referencing before, like starting counting at 0. That's totally cool. So Isaac, you are asking, is there a name for each way of writing it right? Recursive versus explicit. Yes. So this is recursive, and then I would just call the other explicit. So this one, is there any questions on this one? Because I kind of want to talk about this one over here really quick. Let me know if there's any confusion. Okay, so over here, I'm going to let n run from 1 on up. So over here, notice that we needed to reference an a sub 0 that wasn't in our list. Over here, things are going to be okay, because when n equals 1, the left side says a sub 2 equals -1/2 a sub 1. Okay, cool. So here I'm going to set a sub 1 to be my first sequence term. And then it unfolds just like the previous one. If you've done a lot of computer programming, you do this kind of stuff all the time. So like programmers in the class, you've been doing this. Like this is literally like just a little bit of code right here. Pseudocode, right? So any questions on that, friends?
So is that just how you would give your answer then, or like what's the case for this?
Ooh, I'm sorry. Can you ask that question again, Sophie? Sorry.
Yeah, I'm just like, what is the application for this? Like, is this how we would be answering something, or when are we setting a as that value?
Okay. So like are you asking what the question would be here, and then
I get, because in the last one when we were writing the formula where you said like a sub n is negative times the -1/2 to the n,
yes,
that was seeming like the formula. So then if this isn't, like, how does this fit into that?
There are some sequences that are really hard to describe in an explicit form. This one isn't one of those. We saw that, we did it explicitly right off the bat, but I just wanted to address, first off, John had kind of tossed this out as a possible solution, and it is a solution, and sometimes it will be the only way we can proceed. So I just kind of wanted to say, here would be the question. Write a recursive formula for this sequence. And so either of these answers that we have here would be great answers for that question. Does that sound okay? Awesome. Outstanding. Good question. Good stuff. God, I've got this sequence I really want to tell you about, but I don't want to start in 10 minutes. It's like the most beautiful sequence in the world. In fact, holy shit, I'm going to share something with you that I've never shared with anybody else. And it's not the state of my office. I've shared that with many people to their horror. There is a library of weird sequences. So let me see if I can find that. Library of interesting sequences. Like people, oh, here it is. It's the OEIS, Online Encyclopedia of Integer Sequences. I guess I thought it was interesting. Well, I'm going to send you this. If you're a person who likes exploring different things, they've got really cool visualization tools in here, and people submit. You find a cool sequence, you can submit it to them, and if they find it cool enough, they will add it. So let's take a look at a couple others here. Here's a challenge problem. Find a formula, find an explicit formula for a sub n if we have And I'll give, so the first one, let's call it A sub 1. This is going to be 1. A sub 2 is going to be 3. A sub 3 is 1. A sub 4 is 3. And so on and so on. And you can do it with the tools we've talked about. I have to run to the restroom. You know, this is my classic move, but give you a tough problem to check it out. But see if you can do that. I'll be right back. I'm not seeing anything in the chat window, so that means maybe this is still unsolved, which I find very awesome. I'll give you a hint if you want it. Don't look at the screen if you don't want the hint. Here's the hint. That will help. This is cool. See, you come to math club sometime. This is like some math club shit. Puzzles. Forcing you to go to math club. Ooh, here we go. Oh, Cam. Don't look in the chat. If you don't look at the chat, Cam got it. That's good shit. Good work. Okay, no. Cam's got it for us. Cam wins. I don't know. I'll bring in some prize for you on Monday or something like that. But you still have all the glory. This was Cam's formula. See, there's some kind of oscillation going on, right? Let me show you a cool way to visualize a sequence. You can make n the index your horizontal axis and the sequence value your vertical axis. We're going to be doing a lot of this. So when n is 1, I've got 1. When n is 2, I've got 3. And then I've got this bouncing back and forth forevermore. When you see that kind of behavior, a -1 to the end can be the thing. Yes, they do. Yes, Isaac. Many people find this fun. I'm glad you do. I hope you can tell how fucking excited I am about it too, because this is like one of the best things in the world, just studying lists of numbers and looking at their rhythms. So if you look at this, you can almost get a little bit of info that would help with this. Notice that 2 is right in the middle. And when you see this picture, you can get you can grok a little bit of insight. So here we just see that there's a -1 and a +1 and a -1 and a +1. And I'm not sure what Cam's thought process was on this. But I think that picture definitely helps. So friends, that's all I wanted to tell you today. I wanted to warm your brains up for this stuff because this is what's coming. And then here's a little teaser for the future. What is this list? What does this add up to? Does it add up to anything? What does this add up to? What does this add up to? Oop. Now, I'm not asking you to answer these because the first two for us, the first two for us are going to turn out to be, they don't add up to anything. But there's another way to look at it from an Indian mathematician, Ramanujan, taught himself math. This is in the 1900s, taught himself math, worked with these sequences, these sums like this, came up with some strange answers, turned out to be right by physics later on. So like for us, what do you, what does it seem like 1 + 2 + 3 + 4 + 5 + 6 would add up to? It seems like it just keeps getting bigger, right? He was so cool. So Isaac knows about him. Awesome. It seems like it would just keep getting bigger and bigger. Ramanujan came up with this number. Yeah, there we go. That's the furrowed brow I'm looking for, Abraham. That's right. That's the stuff. He came up with that number. That makes no sense whatsoever. Turns out there's some stuff in physics and higher math that actually agrees with that. This one up here, let me just show you how messed up that is. What if I group the first two together and then the second two together? So, associate. This is the associative property. Looks like that would be 0 + 0 + 0. Looks like it would add up to 0. But if I hold off on that first term and then just start grouping after that, looks like I'm going to get 1 + 0 + 0 + 0 = 0, which is right. Does it even make sense to talk about this? Turns out Ramanujan came up with a half for that one. So, which is actually, this should say 1 here, which is the average of those two. All right, I've taken too much time here, but I have at a minimum got Isaac stoked, and maybe so stoked Isaac will come to class. That would be awesome. So not like I was waiting for, I'm not that stoked. Oh, please come. So friends, shoot me any emails. You have any last minute questions on your exam over the weekend? And otherwise, don't forget, those are due at the start of class. Please, please, please. If you're not going to make it to class, send me a PDF before then. Have a beautiful weekend. Thanks for coming. I got all the participators recorded, so EC extra credit for you.
I got a
Thank
question.
you.
real quick.
Okay, cool. I'll hang out. Yeah.
It's just easy. Do you post your Zoom videos on YouTube or?
I do. I think I forgot to post the last one, but I will be posting this. Yeah.
Cool. Thank you so much. Have a
You're
good
welcome,
one.
Gabe. Absolutely. Are we hanging out together, you and me, Ellis? Bye.
I have a quick question really fast.
Cool. There's someone here. So who's that? Is that John, hey,
Everett, yeah. Is it still being recorded, by the way?
did you want me to shut it off?
Yeah, it's just about the test, so I